The International Space Science Institute's Game Changer seminar series, where we look at missions that changed the game in the space sciences. And I am again Tilman Spohn. I'm your host here at ISI in Bern, Switzerland. Today we continue the seminar series with a talk on Rosetta, ESA's planetary cornerstone mission to Comet Churyumov-Gerasimenko, or Jury for short. Before I introduce today's speaker, let me remind you of the program of next month. In October, after we had 7 talks on planetary exploration missions, we'll change gears a bit with talks on the sun, like next week's, and the magnetic field and plasma in the solar system, all moderated by my colleague Rudolf von Steiger. But on October 8, Friends of Planetary Exploration Missions, note that there will be a talk on Dawn, the Dawn mission to Vesta and OSIRIS by Carol Raymond. Another reminder, if you missed one of the previous talks, they are available as recordings on our website, as will be from tonight on this talk. Now, it's my pleasure to introduce Professor Jessica Agarwal as the speaker of today's seminar. She is, since May, congratulations, Jessica, Lichtenberg Professor at the Technische Universität Braunschweig, and she is an expert on small bodies in the solar system. She is the discovery of the first active binary asteroid using the Hubble Space Telescope and has been a member of the OSIRIS camera team on Rosetta. Jessica, the floor is yours. Thank you very much for coming.
Yeah, thank you, Tilman, for the introduction and for inviting me to give this talk. The talk will be on the Rosetta mission to Comet 67P Churyumov-Gerasimenko. And you can see here an image that was obtained by the OSIRIS camera towards the end of the mission. And at the bottom, you see a very short a small part of the surface reflecting sunlight, and then a lot of dust grains in the coma above the surface. And this is a very typical view of the comet we had for more than 2 years while Rosetta was following it through perihelion. So I will begin this talk with a short introduction on comets, what they are and why we are interested in them. Then I will introduce the Rosetta mission and its target comet, 67P Churyumov-Gerasimenko. And then I will talk about several aspects which are very personal selection, aspects on which I think that Rosetta gave us significant new information on comets and on Comet 67P. And I would like to stress that this is a personal selection, so to cover all the groundbreaking results that Rosetta made in these 2 years is I think impossible in 45 minutes. And I apologize to everybody whose results are not mentioned here. Comets are small bodies in the solar system, so they are roughly 1 to 10 kilometers in size. And we think that they are remnant planetesimals. So they formed in the early time of the solar system before the planets. And they probably contain material that was later included into the planets, except for the comets that we still have, which were not included into planets. So this is a drawing by NASA of our view on how the solar system formed. So it formed 4.6 billion years ago from a cloud of dust and gas, as you can see on the left. And this cloud collapsed to a disk, and material collapsed further into the center, where then the sun formed and started burning. And the remainder of the material formed a disk, and in this disk, it formed larger and larger bodies. So first planetesimals, and then finally the planets. And we think that comets and asteroids are the remnants of this formation process. And this is one of the reasons why we are interested in comets, because we think that they contain some of the material that has been least processed since the formation of the early solar system, and that comets may contain clues for us to understand how the solar system formed in detail. Today's solar system contains 3 reservoirs of small bodies. That is, so these remnant planetesimals, and that is, one of them is the asteroid belt between the orbits of Mars and Jupiter, where it is comparatively warm, 100 to 200 Kelvin typically. The second reservoir is the Kuiper belt beyond the orbit of Neptune, where it is quite cold, 40 Kelvin. And the third reservoir is the Oort cloud, which is far out at the gravitational boundary of the solar system, where it is even colder. And the planetesimals in the Kuiper belt and in the Oort cloud, they obviously have been stored at very cold temperatures. And this is the reason why they have preserved frozen volatiles. So volatile substances like carbon dioxide, carbon monoxide, molecular oxygen and nitrogen. And they have preserved these substances as ices. And this is one of the reasons why we think that they can provide significant clues to the composition of the early solar nebula. This is a drawing that is already 15 years old, and it shows some models that we had made of comets before we went to explore them with spacecraft. So our idea is that cometary nuclei contain frozen volatiles, as I just said, ice, and dust, so refractory material that has much higher sublimation temperatures, and that somehow they are a mixture of both. And there has been, and there is still ongoing, a debate which material dominates. So if they are icy dust balls or dirty snowballs. And we also don't yet really understand on which scales these materials are mixed. But what we know is that, yeah, comet nuclei contain, on the one hand, frozen volatiles, ice, and mainly water ice actually, but also smaller amounts of other ices, and dust. And this dust consists mainly of silicates and carbonaceous components. So these comet materials are stored below 40 Kelvin in the outer solar system, and they are catapulted in the inner solar system from time to time when they encounter one of the outer planets or even a neighboring star. So by gravitational perturbation, they can leave their reservoirs in the Oort cloud or the Kuiper belt and then come to the inner solar system. And comets that come from the Oort cloud we call long period comets, because they traveled a long way and have very long orbital periods. And comets that come from the Kuiper belt eventually can end up on orbits that have their aphelion close to the orbit of Jupiter. And in this case, we call them Jupiter family comets. And then they have short orbital periods below 20 years, typically of order 5 to 10 years. And they all have quite low inclinations. So they are more or less close to the ecliptic with their orbits. And Comet 67P is one such Jupiter family comet. Hence, it has come from the Kuiper belt to us. When such a comet enters the inner solar system, it gets warmed by solar heating, by solar irradiation, which you can see coming from the left in this image. And then the volatiles sublime. So they get heated, they transform to gas, and the gas streams away from the comet into empty space. And it carries along with it the dust that is embedded in the comet nucleus. And this means, so you have a small comet nucleus here at the bottom of this image. You see the nucleus of Comet Halley that was imaged by the camera on the Giotto mission, ESA's Giotto mission. And this nucleus gets then embedded in a coma of gas and dust, so like a transient atmosphere, which is not gravitationally bound. And the dust that is carried along by the gas, finally, when the gas becomes too diluted at large distances from the comet, then the dust gets picked up by solar radiation pressure and it is driven away by solar radiation pressure. And then it forms this bright dust tail that we know of comets and that sometimes we can even see with the naked eye. And the dust, we see the dust because it scatters sunlight. So what we see is scattered sunlight by dust. And then comets also can develop a plasma tail, which consists of ionized gas, and that which is carried along by the solar wind. Before Rosetta, we have spacecraft have visited 5 other comet nuclei. So at the top right, you see Comet Philae, which was the first comet to be visited by several spacecraft in the 1980s. And then you see 4 comets, Tempel 1, Borrelly, Wild 2, and Hartley 2, that have been visited by NASA spacecraft in the early 21st century. And now I would like to come to the Rosetta mission. So Rosetta was an ESA Cornerstone mission, as Tillman mentioned, and it was launched finally with an Ariane 5 launcher from Kourou on 2nd of March 2004. And this was after a phase of almost 20 years of preparation. So the first proposals for Rosetta were written at the time of the Giotto encounters, and then it took 20 years to prepare the mission and to build the instruments. And after the launch, Rosetta spent 10 years cruising the solar system before it finally reached its target comet. So you can see here the very complicated trajectory, which was so complicated because the comet is on a very elliptic orbit. And in order for Rosetta to be able to follow the comet on its orbit rather than only to fly by it, Rosetta had to adapt its orbit that came from 1AU, from Earth, to become as eccentric as the comet's one. And in order to achieve this, Rosetta had performed several swing-bys, so gravity assists by Earth and by Mars. And on its way, it even studied 2 asteroids. So it flew by 2 asteroids and took scientific measurements at the asteroids. And finally, in 2014, it reached Comet 67P. That is the number 8 here on the orbit. So, number 8, yeah, that's the arrival at the comet. And then it started to observe the comet. And then after some time, which is not depicted here, quite early in the mission, it deployed a lander to the surface of the comet. And then it kept following the comet through its perihelion passage. So the white line here is the comet of the orbit, and Rosetta followed the comet's perihelion passage all the way through through perihelion, so its closest approach to the sun, and back out to almost 4 astronomical units till the end of mission in 2016. So with this, Rosetta was the first mission to not only fly by a comet and take a scientific snapshot of it, but to follow it and see its evolution while it approached the sun, got heated, became active, and then receded again from the sun, and while activity died down. So Rosetta was able to witness the evolution of the comet as a consequence of different heating conditions and different illumination conditions. And it was also able to witness the changes that the perihelion passage induced on the surface of the comet. And this is one of the unique aspects of Rosetta. Rosetta was a very complex spacecraft. It carried 10 scientific instruments on the orbiter, and they were very diverse. There were 3 dust instruments. There were several spectrometers, so a mass spectrometer with several subcomponents. There were an ultraviolet, a near-infrared spectrometer. There was a submillimeter instrument. There was a camera, a scientific camera, and a navigation camera. There were a plasma instrument and a magnetometer. And there was even a Comet Nucleus sounding experiment, so a radar, a ground-penetrating radar that was had 2 components, one on the orbiter and one on the lander. So in addition to all these scientific instruments on the orbiter, Rosetta carried a lander, Philae, that you can see here in blue towards the bottom of the spacecraft. And this lander carried again 10 scientific instruments of its own, and that were designed to study the surface of the comet in detail. And yes, one of the instruments was on both the lander and the orbiter in order to study the interior of the comet through radar. That was concept. Here you see a quite complicated plot of the orbital evolution during the Rosetta mission, both of the Comet and of Rosetta. So you have the timeline on the horizontal axis from the first approach to the comet in August 2014 to the final landing of Rosetta in September 2016. So at the end of the mission, also the orbiter was landed on the surface, landed in quotation marks. So it was gently lowered to the surface and took scientific measurements until the very end. So the mission started at 3.6 astronomical units when the comet was still had a very low level of activity. And Philae was deployed at 3 astronomical units, which is the point where activity, especially water sublimation, begins to increase significantly. And after that, the orbiter mission went on towards perihelion at 1.2 astronomical units, and then continued until 3.8 astronomical units. And the red line you see here is the distance of Rosetta to the surface of the comet. And you can see that this changed a lot during the mission. And there was a phase early in the mission when this distance was between roughly 10 and 30 kilometers. And this phase was used to map the comet, to get to know the comet, also in order to study the landing site, to find a landing site first. And then the distance increases because the activity of the comet forced the spacecraft to retreat to a safe distance. So during the perihelion passage, the typical spacecraft distance was of the order of 100 kilometers from the comet, which of course affected the resolution of the cameras and spectrometers in particular, but also the ability of the instruments to study the material in the coma. And then when the cometary activity died down again, Rosetta could again go closer, and finally, just before the end of the mission, reached the lowest distances, so very low orbits with a few kilometers distance, and which allowed then very highly resolved measurements of the surface. And then you have a blue line here, which is the subsolar latitude. So it means this is the latitude where the sun is in zenith at a given time. And you see that this goes from positive values, so from northern latitudes to negative values during perihelion, and then back again to northern latitudes. And what this means is that, and I will come to that again with a different drawing, what this means is that during the perihelion passage, so during the time when the comet was closest to the sun, it was the southern hemisphere that was mainly illuminated and got most of the solar irradiation. Whereas while the comet is in the outer solar system and further from the sun, it is the northern hemisphere that is mainly irradiated. So the perihelion passage, the time when the comet is closest to the sun, coincides with southern summer. And this is an aspect that is very characteristic of Comet 67P, and that also drives its pattern of activity and erosion. And that has become to be very, very important for our measurements and the interpretation of our measurements. Yeah, this is one slide about the landing of Philae. Because Philae landed several times. This was unintended. The original idea was to land it just once in the Agarwal site that you see just at the bottom left of this image. But it actually rebounced off the surface in that place and then hit the surface probably twice before it finally come to a final landing in the Abydos region, which you see in the middle of the image. And you see here images of the surface at the different sites. And in particular, I would like to point out the difference between the first and the last landing site. So between Agilkia, which is covered in fine-grained loose material that probably has fallen back from the coma to the surface, whereas Abydos is characterized by what we call consolidated terrain. So this is much more coarse and less dusty terrain, and possibly more representative of the subsurface of the comet, so of the actual interior of the comet. So by this hopping on the comet surface, which was not planned, of course, some measurements have been negatively affected, but it also allowed the lander team to study 2 landing sites and to demonstrate that comets are not homogeneous, not on any scale. So this comet is very different in different places, looks very different. And this, I think, is also one of the key messages from the Rosetta region, that there is not the comet, and it is very difficult from average properties to deduce the detailed physical interpretation. So if we look at the comet with a telescope, we only see it from far away and see an average, and we miss a lot of the detail that may be important for its detailed interpretation. Now I come back to 67P Churyumov-Gerasimenko, which you already have seen right now, but I would like to start from the beginning. So it is a Jupiter family comet, as I already mentioned. And here you see a model of its orbital evolution as a function of time and going backward. So it is very hard to model the orbital evolution over long time scales. But what you see here is that until roughly the early 1900, 1920, it had a perihelion distance of 3 AU, and it stayed at roughly 3 AU until 1959, when it had a close encounter with Jupiter, and only then did its perihelion distance shift to the 1.2 to 1.3 AU that we have today. So probably until 1960 or 1959, it has been heated to a lesser degree than we can see now. And this is a telescope image. So this is a typical image of a comet that you get from a ground-based telescope. And you see the coma and the long tail, you see the dust. And before Rosetta's arrival, this is about the information we had on 67P. We could deduce several aspects. So we could deduce the size, we could deduce its activity, level of activity roughly. We could even deduce to some degree, the change of activity with time, and had thought we had an idea of the shape. But yeah, the actual shape that we saw when Rosetta arrived at the comet surprised, I think, most of us, because we had not expected it to be a binary, actually a bilobate nucleus. So 67P consists of 2 lobes, 2 parts that are connected only by a very thin neck. And yeah, this was one of the first big surprises to us. Even though we had known that comet nuclei can be bilobate and can seem to consist of 2 different parts connected. But the fact that this neck is very thin on 67P had not been seen before. And here's a few numbers or a few very superficial facts. So 67P has been found to have a bulk density of 500 kilogram per cubic meter, which is half the density of water ice. And given that the comet mainly consists of water ice and refractory materials, so silicates, and carbonaceous components, this implies that it must have a very high porosity, and the estimate is that the overall porosity of the nucleus is about 80%. So 80% of this volume are actually void. The gravity compared to Earth is tiny. It's 1/1,000,000th part of Earth's gravity. And the same holds for the gas density near the surface. Also, that is much, much lower than we have in our atmosphere here. And then the comet is dark. Comets in general are dark, and the albedo is of order of a few percent, even though they seem very bright in telescope images. They are actually among the darkest objects in the solar system. And 67P's rotation period is of the order of 12 hours. And the next images are just to give you an impression of what the surface looked like and what we found, and of typical structures we saw on the surface. So you see here both lobes and the neck that connects it, and you see wide areas of what we call fallback material, this loose dust-like material that covers wide areas of the surface. And this is material that probably was lifted at some point from the surface and then fell back because its velocity was not high enough to make it escape from the gravity field of the comet. You also see a very steep cliff, that's the Harter cliff. And it's the highest cliff on 67P, but actually 67P has many more cliffs of lower height. And cliffs seem to play a very important role for the erosion of the comet and for its activity. And then you see many circular features, and a very prominent one I pointed out there in the middle. And I think the origin of these circular features is not ultimately resolved. They probably somehow relate to the activity, so to the outgassing of the comet, rather than to impact features. Here again, you see the Harter cliff from a different perspective, and you see the loose debris that is at its foot. And you see also in this image that there seem to be layers and fractures on the cometary surface, very much like on Earth, actually. And I will come to this layering later in this talk. Here you have a different view of the comet, again pointing out the smooth terrain on this vast plain on the right-hand side, and an example of consolidated terrain on the left-hand side. And you see the diversity of the terrain in this image very well. You see also boulders lying around in the front of the smooth terrain. And yeah, so Rosetta also showed us that comets are really geological objects. So I think it introduced a new discipline to comet science. That's comet geology in a sense. And here finally you see close-up views on fractures. So the consolidated terrain is often characterized by these fractures that may be a result of thermal erosion, because the comet surface suffers huge gradients in temperature between day and night. So it gets very cold at night and can get very hot during day. And this may stress the material and make it fracture pretty much like on Earth as well. Now I would like to talk more again about seasons on the comet. So here you see a drawing of 67P's orbit, the elliptical orbit, and its equatorial plane as compared to the ecliptic plane. And no, the orbital plane is roughly aligned with the ecliptic, so it's actually the orbital plane. So the rotation axis is very much inclined with respect to the orbital pole, which means that as I said before, the southern hemisphere is exposed to the sun during the perihelion passage, whereas the northern end, which so experiences a short but very warm summer, while the northern summer is longer, but less intense, so colder, because the comet is further away from the sun. And this is, so this difference in seasons is a result of the high eccentricity of the comet orbit and of the particular orientation of the rotation axis. So this may be very different for other comets. You can conceive a comet where both hemispheres experience the same amount of illumination and irradiation, even though they are on eccentric orbits. That then depends on the orientation of the rotation axis. And since the seasons have been found to be so important for activity on Comet 67P, it also means that comets can be very diverse depending on their individual orientation of the rotation axis, and actually also on the individual shapes. So this is a model showing the expected erosion of the comet surface from the amount of irradiation it receives. So blue colors correspond to low erosion, and red colors correspond to a high degree of erosion up to 20 meters. So the color range is from 0 to 20 meters. And this shows very well that the north erodes maybe by a few meters, whereas the south is expected to erode much more, up to 20 meters in this model. And therefore, this introduces a dichotomy on the comet. So it selectively erodes one of its hemispheres. And here's a drawing of what the consequence of this is. So in the summer hemisphere, which is shown on the left, you have a high gas pressure. So a lot of material is lifted from the surface by the high gas pressure. But the largest grains or chunks that are lifted from the surface are not fast enough to escape the gravity field. And so they will enter orbit about the comet or be on a parabolic flight and then fall back to the surface. And they typically will fall back in regions that are less active. So in the winter regions, essentially. So because there the gas pressure is low enough that they can actually reach the ground. So you have a seasonal material transport from the summer to the winter. And since southern summer is more intense than northern summer, that probably means that there is a net mass transport from the southern hemisphere to the northern hemisphere. And that therefore the southern hemisphere also is more pristine and less dust covered than the northern hemisphere. So we try to study this also in images, and there have been many examples shown that of the erosion of the southern hemisphere during the perihelion passage. And here you have one example where on the left you see an area that is actually dust covered. So there are these three big circular features, and to the right, where the arrows point, there's an area that is covered in dust. And this dust cover, so the left-hand image is from November 2014, about the time of the landing of Philae. And the right-hand image was taken 1.5 years later, after the perihelion passage. And you see that this dust cover has vanished, and that you see now boulders that were previously hidden below the dust cover. So indeed, the activity during perihelion removed several meters of dust cover from the surface. And this, by contrast, are examples of the fallback that you see on the surface ubiquitously. To the left is a broader view of a larger area on the comet, and the right one is actually a very close-up view taken by the camera on Philae, the Rollers camera on Philae, with a very high resolution, where you see a larger boulder half hidden by smaller dust grains. So this is the material that then falls back to the comet surface. And a more global analysis of the colors of the comet, so by the spectrometer Wirtanen, shows that the spectral color changed between large distances and close to perihelion. So when we approached the comet, the comet had a reddish spectrum, and when it came closer to the sun, the spectrum became relatively bluer. So the comet didn't really become blue, but the spectrum became less red. And this is an indication of an increased amount of water ice present near the surface. And this bluish color changed then back to a reddish color, to the original red color, when the comet left again the perihelion passage and went to distances further from the sun. And at the top you see a schematic drawing of this, and at the bottom you see the actual spectra. So the horizontal axis again is time. So this is the essentially months of the mission, into the mission. And the vertical axis is the spectral slope. And a large value means a redder spectrum, and a small value means a bluer spectrum. And this analysis here that is shown here shows analysis for 3 different regions on the comet. The analysis was taken for more regions, but I show only 3. And you see that towards perihelion, the spectral slopes goes down and becomes bluer. So this is also an indication that with increased activity, the surface we see is less covered in dust, but probably is more comparable to what the interior looks like. So it's more ice rich. Now I would like to briefly talk about activity. So for us, it is still difficult to pinpoint where actually dust and gas leave the surface of the nucleus on a regular basis. So we know that when the comet rotates, you see all these structures in the coma. When the comet rotates, these structures change, but then after 12 hours, when the comet comes back to its original positions, the structures look more or less exactly the same. So there is a regular pattern of activity at the surface of the comet where outgassing induces the dust to be lifted. But it is still very hard for us to really pinpoint where these streams of dust come from on the surface and why they form these patterns. And one of the reasons of this is that we could only observe the dust in front of the dark space, but not in front of the nucleus, because the nucleus is much brighter than the dust. So we only see the part of the dust that has already left the nucleus and not its region. It is very hard to reconstruct the origin on the surface of the dust. And we also have actually an increasing amount of conceptual questions of how the dust can be lifted, because the dust grains are held together by a cohesive force that needs to be broken by the gas pressure, and the numbers in our models do not always match. So this is very much an open field of investigation still. We have a lot of data from Rosetta, but I don't think we have final conclusions on this yet. One thing that Rosetta has shown is that there are probably different forms of activity. So different ways the comet loses mass. And I would like to give one example of these here, and this is the collapse of cliffs. So on the left-hand side, you see the image of a cliff, the Aswan cliff, as we call it. And in particular, at the bottom left, you see, indicated by this yellow arrow, you see a fracture near the edge of the cliff. And then in the middle, you see a bright outburst. We call it outburst when suddenly the coma brightens. So suddenly a lot of dust is ejected into the coma and makes the comet become very bright for a short period of time. And this happened on 10th of July 2015, and the origin of the dust cloud could be reconstructed to be somewhere in the area of this Aswan cliff. And then later we could again image the Aswan region, and we saw this very bright spot on the surface in the place where before the fracture had been. So you see that on the top right image, again indicated by the yellow arrow. So there, part of the surface of the cliff had broken away and probably gave rise to this very bright outburst. And then these are again two images of the cliff, and especially the right-hand side image was taken after the outburst. And you see that this part of the cliff where at the top there is this piece missing, this part of the cliff is very bright. And brightness always indicates a higher fraction of ice content. So probably this collapse of the cliff, or this breaking away of part of the cliff, revealed a portion of the interior of the comet that is still more rich in ice than the surface that has been exposed to sunlight for a while. So this collapsing of cliffs is one form how the comet remains active. Because one of the questions, of course, is how can it remain active when there's always a dust mantle forming, either by fallback or by sublimation of ice. And cliff collapse is one way to keep fresh surface exposed to sunlight. And coming back to the outbursts, we have seen very many outbursts during the Rosetta mission from the very beginning, just even before we reached the comet, to the very end. So, and they have been, very different in shape and in their source region of origin. And I think we still need to figure out how they came into being, what caused them. Activity is also capable of moving large boulders across the surface. So here is an example of a 30-meter sized boulder that was moved across the surface over a distance of less than a year, time distance of less than a year. And now I would like to briefly talk a bit about the interior structure. So I already mentioned that we saw that the comet subsurface seems to be layered. And here we see a terrace-like structure that seems to reveal different layerings in the interior of the comet. And then scientists, Masironi et al. And Penasa et al. Went and investigated the orientation of these layers, of each individual layer, and then connected the individual orientations of the individual pieces of layer of the terraces to a global model of the layering in the interior of the comet. And you see at the bottom right that the layers can connect it by onion-like shells in the interior. So if the interior is structured like an onion and you cut off different pieces at the surface, then you would get this terrace-like structure that we observe. And the final model shows that probably the two lobes each have their own onion shell structure. So the conclusion is that probably these two lobes formed independently of each other, or at least the layering was induced independently into both of them before they merged to become a bilobate single comet. So the alternative hypothesis would have been that the neck formed by erosion, by some process of erosion, and that originally there was one single comet, but from the layering it seems more likely that they were two objects that later on merged. And this is a very brief overview of the derived mechanical properties of the cometary surface. Well, the blue lines are from Rosetta, and then there is laboratory experiments, modeling, and Rosetta, and results from other space missions. And the horizontal axis is a logarithmic scale of the strength, so different types of strength: tensile strength, compressive strength, and shear strength. And the main purpose of this slide is to show you that our measurements are very diverse. So depending on where the measurements was taken and which method was used to measure the strengths, we get very different results. And this may either reflect the diversity of the cometary surface or the diversity of our measurement methods, or both. And I think this is also very much ongoing work, and I don't think we have reached a very final conclusion to this. But the overall impression is that the strength of the material is rather low, so sub-kilopascal probably in most measurements, but not zero. Now I would briefly still talk about dust and gas, although time is running. So here are a couple of microscopic images obtained by the COSIMA instrument. So COSIMA was a dust collector which collected dust grains on the surface, and then both could take mass spectra of the dust grains, but before taking the mass spectra, it could also image these dust grains with a microscope. And you see that the dust is very porous, fluffy, and it looks like by sticking to the surface, it formed a pile, so it probably changed its structure and sort of collapsed in itself. So it consists of smaller aggregates that down to the resolution of the microscope actually. So the smallest entities may not have been resolved by COSIMA. And then there was an atomic force microscope on Rosetta as well, the MIDAS, that had a higher spatial resolution. So it could resolve the dust grains down to micrometer scales and saw this aggregated porous structure also on these scales. So we probably did not resolve the finest level of aggregate structure, so the smallest grain entities of which the dust is formed. And here's an example of mass spectra taken by the Rosetta instrument. And it is mainly to show that there is a very, so Rosetta and also other instruments found a very complex organic chemistry in the comet, both in the gas phase and on the dust, although they were different kinds of molecules. And one of the inferences is that comets may actually have brought such molecules also to the atmosphere of Earth, and that they, so these are maybe prebiotic molecules, but I think detailed inferences are also still work in progress. And finally, I would like to point to the measurement of molecular oxygen by Rosetta, and which came as a surprise. So molecular oxygen is highly reactive, as you can imagine, and needs very cold temperatures to remain in its molecular form without reacting with other material. So Rosetta found that there is a significant abundance of molecular oxygen, almost 4% relative to water, and that oxygen and water are correlated, highly correlated. So wherever you have a lot of water, you also have a high amount of molecular oxygen. And this is different, for instance, for carbon monoxide, which is also highly volatile, but which is to a lesser degree correlated with water. And you also have molecular nitrogen, which also needs a very cold environment, but also was less correlated with water. And one of the safe conclusions from this is that this comet must have formed in a very cold environment and also have been stored in a very cold environment, or at least its interior must have been stored at very low temperatures for its whole existence. And it probably also provides additional constraints on the chemistry in the protoplanetary disk. But this is beyond my expertise, and I think it is also ongoing work. So with this, I would like to come to very brief conclusions. So as both to key results and key open questions, and both are strong selections and by no means complete. To me personally, one of the key results is the importance of seasons and the shape of an individual comet for its pattern of activity, which means that if we take an instantaneous observation of a comet, be it by a spacecraft flyby or be it by a telescope, this may not be representative of the whole object because it is only a snapshot. And as these comets, they evolve very much as they travel along their orbit. Another pretty firm conclusion from the Rosetta mission is probably that 67P formed from two separate objects. And another key result is the unexpected chemical diversity of the comet. And there are many, many more concerning activity and interior structure and many things. And the key open questions to me, or some of the key open questions to me, are how does activity and erosion work at the surface? So how is the surface changing with time? Because this, if we don't, we need to understand this in order to understand the interior structure of the comet. So only by understanding how solar illumination changes the comet, we can also understand how the comet would look like if it were not irradiated by the sun. And understanding the interior structure and interior composition of the comet is something we need in order to finally answer the question of how comet nuclei formed in the early solar system. And currently there are two, say, competing models or two different models of how comet nuclei formed. One is the hierarchical accretion model, where the comet accreted slowly, step by step, in the protoplanetary disk. And the other model is the so-called pebble cloud collapse model, where you have a large amount of centimeter-sized dust grains that finally collapse under their own gravity. And distinguishing between these two models or third models in between or alternative models is of course one of our ultimate goals with studying comets. And with this, I'm at the end of my presentation, and thank you for your attention.
Thank you very, very much, Jessica, for this nice and clearly presented talk. Thank you very much. For the audience, you have two ways of posing questions. One is you just enter a question in the chat channel, and I will read it then to Jessica. And the other possibility is you raise your hand, and then we will give you the mic. I'll start with the chat channel because the questions have been posed there already. And then we'll switch to the raised hands. So Megan Russell asks, how large are the boulders in the visible images, just for an idea of scale?
I think they are down to our resolution. So most of the boulders you saw are probably typically several meters sized, but they are also larger. And yeah, they go down to the limit of our resolution, which is probably sub-meter sized, centimeter sized.
Okay, Hugh Hudson asks, I understand that this may be uncertain, but what is a rough number for the mass loss rate, and how would this change with orbital phase?
You mean the mass flux rate from
mass loss rate?
Mass loss rate.
Yeah.
So it changes with orbital phase. It changes by several orders of magnitude, but I must admit I don't have the number in my head now. Okay.
Keith Horn, what processes forms the layered structure? Is it episodic accretion of material or perhaps repeated heating episodes?
I think we don't know.
We don't know.
I don't know, and I think also I haven't seen a firm conclusion in the literature. So there are several models, but I don't think we have a final answer. But 67P is not the only comet with the layered structure. We know at least of one other comet that also showed layering. That's Comet Tempel 1.
Okay, why don't we switch to the raised hands now and come back to the chat again then after that. So Roger Bonnet is raising his hands, and Roger, please ask your question. Roger, I think, was ESA science director at the time of the selection and much of the mission itself. Roger.
Thank you, Tilman. I hope you can hear me.
Yes,
Sure.
I can hear you.
Okay. First of all, thank you for introducing this game changer in the program. For me, it's one of the real game changers of this field. But first of all, congratulations for your presentation, Jessica. It is wonderful. What you made really moved me. What you presented moved me strongly. Thank you and congratulations for your presentation. I am very impressed.
Thank you.
A million times impressed. I spent 16 years of my life in ESA starting and developing this mission until I left ESA in 2001. Let me say that I am very proud of what the scientists have done with this mission, in particular you, who has given us fantastic vision of the details of the evolution of the comet when it goes close to the sun and back to deep space. I would like also to thank the people who made this possible, all the scientists involved in the development of the instruments, and you, the scientists who analyze the results. Also, I cannot forget the ESA scientific and technical managers who made this mission come through. Again, congratulations 1,000 times for what you said.
Thank you.
Thank you. We move on to Iju Hu. Please ask your question.
Okay, thank you. This is a very nice talk, and I'm very impressed. My question is, so since this comet is going around the sun multiple times already, suppose every time it passing the sun, it will lose some mass, that eventually this comet will disappear. Is that right? Or it has some other way to collect more mass when it is away from the sun?
So I agree. So I don't think it does accrete new mass when it is away from the sun. So you are right, it loses mass with every perihelion passage, probably a couple of meters, maybe. And we don't know what its final fate will be. So there are several theories concerning the ending of comets, and they may all be right depending on the object. So one idea is that comets, the activity of comets is finally quenched by their own dust mantle. So this is what I try to indicate when I talked about the cliffs, that at the cliffs you keep fresh active surfaces, but many other surfaces become either covered in dry dust or more or less dry dust that falls back from the coma, or just lose their surface ices, and what remains is a dry dust mantle. And at some point, this dust mantle may become so thick that solar irradiation may not reach the ice-rich layers in the interior of the comet anymore. So there are objects that are on comet-like orbits, but that don't seem to show activity or show only very low-level activity. And we think that these may be comets in the end state of their activity. So they may end up being just inactive objects that then don't lose that much further mass anymore. And then their orbits may evolve in a way because they are on elliptic orbits, so they encounter planets. So they may either be ejected from the solar system or spiral into the sun and finally burn there. But there's another way of comets to end, and that is by disintegration. So some comets disintegrate spectacularly in many pieces, either in several fragments or in many fragments. Some do this under the influence of tides, under gravity. So you may remember Shoemaker-Levy 9 that crashed into Jupiter. But other comets also do that spontaneously for reasons that we still don't understand. And if comets just disintegrate into larger fragments or finally crumble into small pieces, that would also be a way of ending their existence as a comet and essentially becoming part of the sun's zodiacal dust cloud.
Okay, oh, sorry.
No, there are many ways for a comet to end.
Okay, let's switch back to the chat channel for 2 or 3, and then come back to the raised hands again. So Paul Temmer asks, appreciate your talk. Can you give where did you go? Can you give a short wrap up what happened with the mole experiment? Actually, I think he's referring to the Nucleus experiment. And that's actually my experiment.
So maybe
you want to comment on it?
Maybe you should give the answer to that. You're more expert than I am on this.
Oh, Paul, I call you up and discuss it with you. Okay, SAS asked, from what we have learned so far, do we have hypotheses to explain activity of comets from Oort clouds, such as C2017 K2 at very large distance from the sun?
Yeah, this is a very nice question, because this comet is a very good illustration of this activity paradox I was hinting at. So I tried to mention that dust has cohesion, so that there are cohesive van der Waals forces between dust grains, and gas drag needs to be, or something needs to be strong enough to break these cohesive forces. And the comet you mentioned was discovered at very, very large distances from the sun, so beyond 20 AU astronomical units. And at these distances, not only water is not active, but also several other processes that we think might drive activity in comets are not strong enough to break the cohesive forces we think exist between the dust grains. So one of the possibilities to drive distant activity is the crystallization of amorphous water ice. So water ice can, classical water ice that we know is crystalline, but water ice can also be an amorphous structure. So you don't have a crystal structure, a regular crystal structure. And when this amorphous water ice crystallizes, it releases energy. And this energy might drive cometary activity, but we don't know if the amorphous water ice exists. And we also don't know how much energy it actually releases in a comet interior, because it's a very complicated process and there are many unknowns to it. So I think currently we do not really understand what drives the activity in such distant comets. And it's one of the big questions of our field, I think.
Okay, Neil Turner, what is the status of ideas about the origins of the 100-meter wide pits?
I don't think I don't know the answer. I'm not an expert on this either, but I also haven't heard of a final answer. So I think that is subject of ongoing research.
So let's take one more from the chat list and then go over to the raised hands. So Pavel Krupa asks, thank you for a very nice and interesting presentation. Are there any simulations of planetary system formation which are also seen to form comet-like objects? Yeah. Well.
Yes, I think there are.
Well, they basically enter them as the stuff to make the planets from.
Yeah.
Yeah.
Yes, there are simulations and there are different models. And yeah, I think we don't. So there are different models of comet formation that are both consistent with what we know about 67P. Or put it the other way, we don't have yet enough information about 67P to distinguish between different models.
But I heard that Alessandro Morbidelli, known as Morbi, had to revise his model because of the cold temperatures at which Chury formed. You have a comment on that?
Yeah, I think Chury or 67P results keep providing new constraints to these models, and yeah. Okay. But I think it's ongoing work. And
it's ongoing work, certainly. Yeah. So let's go to the raised hands. Klaus Schilling.
Yeah, thank you very much. It was very impressive, and I joined Rosetta 33 years ago and had the pleasure to coordinate in industry the technology side, system definition studies. Here were different scientific issues raised. One of the big motivations were that comets provide access to pristine material from the origin of our solar system. Now, in your impressive talk, we saw a lot of processing happened on the comet. So dust deposits and erosion and so on. And how much more do we know now about pristine material? That's one question. And I have a second question. Another big motivation was also to learn more about water transport to Earth. And as we know now, the deuterium fraction on the comet is different from what we have on Earth. So how much can we transfer this water question from Churyumov-Gerasimenko to other comets? Or can we exclude that comets have a responsibility for water on Earth?
Okay, so these are two difficult questions, I think. So concerning the pristine material, I think this is what I'm trying to express with my three open questions. So I believe that the interior of a comet is still comparatively pristine. It probably has to be because we see all these highly volatile species coming off the comet. And I also think that, there are models showing that the penetration of solar heat into the interior of the comet is very inefficient. So probably only a very shallow surface layer is being heated. And during periods of strong activity, that means during perihelion in the south, in the southern hemisphere, it is possible that the more or less pristine interior of the comet was actually exposed to space and to sunlight, or relatively pristine. So I think what we see of the volatile species, of the gas of the comet, is easier to relate to the pristine composition than what we see of the dust, because the dust has all this complicated seasonal cycle and mass transport. And so drawing conclusions about the pristineness of the refractory component, I think is very complicated, and I think we are quite far from that for now. That's my personal opinion, but I think hidden in the Rosetta dataset, there is still a lot of information on the processes that reshape the comet at present, so erosion and activity. And I think we can understand still a lot more about these processes. And my expectation is, or my hope is, that by understanding these processes in more detail, we will eventually also be able to disentangle what is a pristine or primordial aspect of the comet and what has been induced by its later evolution or by its current evolution. So I think there is, in the data set, there is still a lot of information to be found. And I think we are still very far from a final understanding of Rosetta data. I think it has the potential for years and decades of further research. That's an attempt at answering the pristineness question. And the water on Earth and I didn't mention the deuterium to hydrogen ratio, because I think it's a very complex topic, and this ratio on Comet 67P has been found to be rather high compared to other comets, and in particular compared to other Jupiter family comets, and also compared to Earth. And my impression is that also in this respect, we don't have a final conclusion. So just by finding that 67P has a different D to H ratio from Earth, concluding that comets were not important to bring water on Earth, I think is probably premature. So these different D to H ratios may also reflect just different formation conditions for different comets. So I think I think this measurement may have made the picture even more complex than we thought before it would be.
Okay, Hans Sinneke has raised his hand. And after that, we go back to the chat channel. Hans Sinneke?
Can you hear me?
Yes.
Can you hear me?
Yeah, we can hear you.
Yeah. Thank you very much. It's again another fascinating lecture during these pandemic times. My question is similar to the one that I asked at the last webinar. It's about the flybys. It was really a masterpiece of space technology, as we have read in the abstract. But still, I am fascinated by the precision of all these many flybys and the fact that the errors would not accumulate. Apparently, there is a correction system that we can be sure that the flybys actually work so well that we arrive at the target.
Okay, Jessica, can you answer, comment on this? Or?
So I would have asked back which flybys Hans was talking about, whether he meant the flybys at 67P or the other comets. So for 67P, I can answer that. Yes, there was an active, so the orbits or orbit segments about the comet have been actively planned and controlled all the time and commanded by ESA, by the European Space Operations Center. So yes, there was a strong active component there. That we did not just enter orbit and stayed in orbit like we can do about the planet. We had to actively plan and correct each part of the trajectory.
Okay, move back to the chat channel. Charlotte Götz asks, if seasons are so important, will we be able to learn something about the surface evolution at all from a single snapshot, like the one that Comet Interceptor will provide?
Well, I think we can learn something. I mean, we now know that seasons are important, and Comet Interceptor will at least show us the rotation state, so we will know the distribution of seasons. And with our knowledge from 67P, we can then reconstruct what seasons might do to the target comet of Comet Interceptor. And just this knowledge and this awareness of the influence of seasons will help us to interpret the data that we get even from the flyby, even though we do not see the actual effect of the seasons because we have only a single time measurement. We know that the effect exists and we can take it into account.
We'll always learn something, I guess. Shinji asks, does the gravity field play a significant role in the long-term formation of the comet? For example, the lateral mass transportation? So
the comet's gravity field, yes.
Yeah.
Because the comet's gravity field is responsible for the fact that dust is falling back to the surface. Mm-hmm. I mean, the fact that there is a gravity field. I don't think that the inhomogeneity of the gravity field played a major role in distributing the fallback, though. I think that distribution was mainly induced by the shape and by the different outgassing patterns induced by the different illumination conditions. Although there are also, there are gravitational lows and highs, and we see that, for instance, in the neck region, which is a gravitational low. So the gravity is this particular low there that material accumulates there. That we do see, yes. So it has some effect.
So Masaki Nishino asked, a really great talk. I wonder whether this extremely low albedo surface is related to carbon atoms.
Yes, probably.
Aiju Hu, I'm pretty sure I mispronounced that. Apologies. The size of the comet seems similar. Does this mean they formed at a similar time?
The size only probably, I would not relate the size to the formation time necessarily, but there are other indications that the two lobes are very similar. So they seem to have the same similar density down to our measurement abilities, and the composition seems similar. So we didn't see any strong differences in the gas composition, for instance, or also the activity. So we didn't see any strong differences between the two lobes, so which probably points to similar formation conditions.
Oh, Anastasios Xoxinas has a question. First of all, congratulations for the presentation. But can you possibly tell us if the erosion models, as the one you presented, are in accordance with the erosion seen during the mission, images, etc.? In other words, is the 20-meter erosion a realistic number? And how much does it take for the comet to lose 20 meters of dust?
So I think it is difficult to study the erosion level from images on a global level. I think that the 20 meters may be a bit optimistic or a bit on the high end, but we see, so we can only measure there are two ways to measure the erosion rate. One is to make a three-dimensional digital terrain model, both at the beginning and at the end of the mission. So we take images from different perspectives and then put them together in a computer model to reconstruct the three-dimensional terrain. And we can do this only from very highly resolved images, and obviously also from images that were taken some time apart. And the trouble with this is that we have such images mainly from the northern hemisphere. If you remember the plot I showed, we were close to the comet at the beginning and at the end of the mission, when the northern hemisphere was illuminated. So for the southern hemisphere, we lack both the time coverage and the resolution to really study this aspect in detail, because we were at beyond 100 kilometer distance from the comet when the southern hemisphere was illuminated. So it is difficult to reconstruct the erosion from the shape model that we construct from the images, especially for the most active part of the surface, the southern hemisphere. So what instead people do is they look at images like the one with the boulders I have shown, where dust is added or removed from the surface. And then you can reconstruct the size of these boulders from three-dimensional viewing geometries and from the distance to your camera and things like that. And then you can estimate the height of the covering dust surface or the height of the material that was eroded. But I'm not aware that there's a global estimate or a global measurement of the rate of erosion. But I would think it's rather on the scale of several meters than on 20 meters.
Okay, another question from the SAS Observatory in Italy. Do you know at which velocity were the emissions outgassing from the nucleus?
So the gas velocity typically is of order 500 to 1000 meters per second. Mm-hmm. And the dust velocity is much smaller.
David Valls-Gabot asks, what about the 016-018 ratio?
I think I'm too little expert to answer this. It was measured.
Okay. Jan Borowicka, the Philae final landing site seems to contain the strongest material encountered in comets. Was it ice or rock?
I think it was both, but I think mainly it was. So there is a theory that that there was ice close to the surface that made it so solid, so hard. But again, I'm not enough expert. I'm not even sure that there are really data to give a final answer to this.
So since I'm responsible for that value on your graph, that is the highest of those. These values of 10 to the 6 are consistent with ice. They're actually consistent with hard snow. You know, it's not so outrageous. It's not rock. Okay. Masaki Nishino has another question. Has the electrostatic force been taken into account when considering the dust particle transport at the 67P Nucleus surface?
I'm not aware of a model. I mean, no, I don't think so.
Okay. Now, Hans Sinneke has raised the hand again. Hans, is that by intention? Please then ask the question. Follow-up question, maybe?
Mistake.
Sorry?
Was by mistake.
Oh, by mistake. Okay, then thank you very much. And so, Liva, just close the mic again. Okay, I think we exhausted all the questions in the chat channel and the raised hands. And thank you very much again, Jessica, for this very nice talk. Thank you very much for those who stayed with us for so long. We still have 80 participants. We had 150 at peak. It's been another very nice seminar in our Game Changers series. And stay tuned. Next week, we'll be looking at the sun. Okay, bye-bye and have a good day and good evening wherever you are. Bye-bye.